Hello and welcome back. In this video we'll be building a NOR gate centered around the behavior of two PNP style transistors. Just to prove to ourselves that this circuit will implement the behavior associated with an OR gate, we can look at its input-output or truth table and reading from left to right. Whenever input 1 is low, input 2 is low, the output should be high, which is the state we have right now. Input 1 is low, input 2 is low, and the output LED is high. Moving to the next row, when input 1 is low, like this state, but input 2 is high, the output should be low, and it is. The next row, when input 1 is high, the LED is on, input 2 is low, the output should be low. And the last possibility is input 1 and 2 could both be high, like this, and the output is low. So it mimics the behavior associated with an OR gate. Let's look at the schematic, talk through how this circuit functions, and then build the circuit. The schematic for this circuit is fairly straightforward. We have two normally open momentary buttons. We have 1K resistor with an indicator, input indicator LED, and then we have the same thing on the second momentary button. We'll have two Schottky style diodes, and in the context of this circuit it would be better to use Schottky because they don't take as much of the voltage. It takes less voltage to make Schottky diodes conduct, in this case about 0.3 to 0.4 volts, and given that we're controlling the base of PNP transistors, we want to get as much voltage to the base of those PNPs as we can to pull them high and turn them off when we need to. But just looking at the circuit, we'll have two PNP style transistors. I'm using 2N2907, but you could just as well use 2N3906 or 2N4403s, etc. The type of PNP shouldn't really matter. Then we'll have some 330 ohm resistors, some 10K pull down resistors, a 1K going to an output indicator LED, and then another 10K. In terms of functionality, how does the circuit work? Well, when the two normally open momentary buttons are open, they're not pressed, what's happening with these PNP transistors? That on the emitter of this transistor we have VCC, and in the case of the circuit I'm using 6 volts. So we have 6 volts sitting at the emitter of the top PNP, and then we also have the base of that PNP pulled down to ground through a 10K resistor, making the base of the PNP less than 0.7 volts than whatever is sitting at its emitter, in turn making this PNP conduct. That all you have to do is pull the base of a PNP transistor normally around 0.7 volts lower than the voltage sitting at its emitter, and the PNP will conduct current. Moving from the first PNP to the second PNP, we have the collector of the first PNP connected to the emitter of the second PNP. This is very similar to the configuration you see building an AND gate out of NPN transistors. They're in a series, these PNPs are. Just like in the AND gate scenario, the NPN transistors are placed in a series. But that being said, we have the same scenario with the second PNP as we do with the first, is that the base of it is pulled down 0.7 volts lower than the voltage that will be sitting at its emitter. Well, given that the base of the top PNP is pulled down, that means VCC is traveling across the PNP, it's conducting the top PNP, putting VCC at the emitter of the second one. So we have around 6 volts sitting here, and then that 10K will pull the base of the PNP so that it's 0.7 volts less than the 6 volts sitting at its emitter. It'll actually pull it a lot further down than that, all the way almost to ground. But all we need is 0.7 volts less than whatever's at the emitter the PNP conducts. Meaning that we have VCC, the first PNP is conducting, the second PNP is conducting, there's a fork in the road. current voltage could go toward the 10K, or it has the 1K through an LED. Well, as I've said numerous times, voltage and current's sort of lazy. It'll go the path of least work, or the most of the current and the voltage will go the path of least work. Some will go through this 10K to ground, but the majority will go through the 1K and turn on the output indicator LED. This is the case where both of its inputs are low and the output is high. That's the normal state when you have power applied to the circuit and you're not pressing either of the momentary buttons. Well, what happens when we do press a momentary button? When we push, say, this button down? Well, now we have VCC traveling across the contacts of the momentary button. Some will go through the 1K, lighting up the indicator LED. The rest will cross the Schottky style diode. All it takes 0.3 to 0.4 volts to force the Schottky to conduct, pushing it down to the base of this PNP. And we have a 330 ohm resistor here because we don't want to lose, or we want to lose as little voltage as possible going to the base of this transistor, but we also don't want to source too much current to the base. So 330 ohms, perfectly fine for that. And so we'll have VCC, which is 6 volts. We'll lose 0.3, 0.4 volts here, so we'll have 5.6 or so volts here that'll come down. We'll lose a few tenths of a volt on that 330 ohm resistor and then reach the base of the PNP. Well, no matter what we lose, we're only going to lose, we'll have 5.5, 5.4. You can take your multimeter and check it if you use a 6 volt system, but if you use 9 volt or whatever, all that you need to notice is that you will have enough voltage here to cut off the PNP. You need Schottkys because if you use normal diodes and you drop 0.6, 0.7 volts off of your VCC supply, there won't be enough voltage left to raise the base of this PNP up so that it's no longer 0.6, 0.7 volts lower than whatever's sitting at VCC. So if you have 5.6 volts here, well, that's only 0.4 of a volt lower than VCC, meaning that the PNP won't conduct. Whereas if you lose 0.6 of a volt here and you have 5.4 volts sitting here, well, that's 0.6 volts lower than the 6 volts that would be sitting at the emitter, and the PNP would conduct. So the trick to using this kind of circuit is just always make sure that you're not losing too much voltage when you're pushing these buttons. You can take your meter and just check how much voltage do I have right here, and then how much voltage do I have right here. And as long as this voltage is greater than 0.6, 0.7 volts less than whatever's at VCC, the PNP will turn off, effectively allowing you to make a NOR gate out of PNP transistors. But all that happens, a quick run through, is when neither of the momentary buttons is pushed, the base of the PNPs, both of them, is pulled 0.6, 0.7 volts lower than the VCC rail that's sitting at their emitters. So they conduct, lighting up the output indicator LED. When you push the first momentary button, VCC travels, you lose a few tenths of a volt, or a few tenths of a volt, goes down. There's still enough voltage left to raise the base of the PNP above that 0.6, 0.7 volt threshold that's required for the PNP to conduct. So you cut it off. It stops conducting. The same story plays out when you push this momentary button or when you push both of them. You're essentially, when you push momentary button, you're shutting the PNP off. If there's any questions about that, just let me know in the comments and I'll do my best to address them. That being said, let's build the circuit. Looking back at our schematic, what I've done at this point is just connected the power and ground rails of the breadboard, as well as the breadboard I'm using separates, has an upper set of power and ground rails and a lower set, so I've connected those together with these pieces of wire. I've added the 2 normally open momentary buttons to the board and the 2 PNP transistors. The first thing we'll need to do is connect the upper right hand corner of each of these momentary buttons to VCC. Connecting the upper right hand corner of this first momentary button to VCC. Connecting the upper right hand corner of the second momentary button to VCC. Now we need to add a 1K resistor to the first indicator LED to ground. Then we'll need to add a second 1K resistor to the second input indicator LED to ground. Both of those will be connected on the bottom left side of our momentary buttons. There's the bottom left corner of our first momentary button, the bottom left corner of our second momentary button. This rail, that rail. Add in the 1K resistor. Add in second 1K. Like that. Then we can add in our indicator LEDs, paying attention to which is the cathode, which is the anode of the LED. On the ones I'm using, the flat side, there's a flat side that indicates the cathode. We want the cathode in the ground rail and the anode in the same rail as the 1K resistor. Cathodes in ground, the anodes in the same rail as the 1K. Repeat the same procedure with the second indicator LED. Just like that. The next connection we'll need to make is on that bottom left-hand corner of both of the momentary buttons. We'll need to add a Schottky style diode pointing down the breadboard. We'll need to add in a Schottky to the bottom left-hand corner of the first momentary button and a Schottky to the bottom left-hand corner of the second momentary button. I'm using 1N 5819s. You could use 1N 5817s. They actually take less voltage, the 1N 5817s. I'm on the borderline with these 5819s. So 5817s would probably be a little better, but you definitely, the trick is to use a Schottky that takes less voltage to start it conducting, because you want to get as much voltage from that VCC line down to the base of those PNPs so that you can pull them higher than their turn-on threshold. Let's put those in. I'll put in the first Schottky, paying attention to the indicator of its cathode. In this case, so the one diodes I'm using is indicated by a gray band, and we want that down toward the PNPs. Notice that diode's in a rail above the top left-hand corner of that momentary button. It's not in the same rail as that. That wouldn't work. So then the next Schottky diode, paying attention to the cathode indicated by the gray band, will go in the same rail as the 1K resistor, the bottom left-hand leg of our momentary button. Like that. Moving right along, we have our momentary buttons, our resistors for our indicator LEDs. We have this part of the circuit completed, as well as our two Schottky diodes pointing down toward the PNPs. So effectively, this part of the circuit we're done with. Now we can move to the two PNPs. And the way we'll end up putting this in the breadboard will look slightly different than the schematic. Sometimes that happens. But in order to keep it tidy on the breadboard, sometimes you have to kind of go off the schematic a little bit. But what we need at the emitter of our top PNP, we need a connection from the top leg of this first PNP, its emitter leg, to VCC. Let's do that. This would be, of the two PNPs, here is the emitter leg of the top PNP. We need a connection from this rail to VCC, like that. Now we need to the base of both PNPs, a person could do this at the same time, we'll need a 330 ohm resistor to the base that will connect with a piece of wire to that Schottky diode. Then we'll need a 330 ohm resistor to the base of the second PNP that through a piece of wire will connect to the other Schottky diode. But we'll also need these 10K pull downs connected to the base of the PNPs. Let's see how that looks on the breadboard. First thing we can do is add in those 330 ohm resistors to the base of each of these PNPs. and the base of the PNP is the center leg. And we just add that 330 ohm resistor to the center leg. It's in the same rail, this rail. We do the same thing to the base of the second PNP. 330 ohm resistor to the base in the same rail as the base leg of the PNP. Then, going a little off of the schematic, we just need to pull the base of the PNP down in the normal position when we're not pressing the momentary button, sending voltage through these 330 ohm resistors. We want these PNPs to be conducting, so we need to pull their base leg, that center leg, down to ground. Well, it's just easier than holding perfectly true to the schematic, just to go ahead and hook the 10K in the same rail as the base of the PNP, which is also the same rail that one leg of that 330 ohm resistor is connected in. It still follows the schematic functionally, but it just looks different. But it's functionally identical. It's just more convenient to go ahead and jump the 10K over to ground through the base, like that. We do the same thing to the second, the base leg of the PNPs in that rail, and we'll want to put a 10K to ground, pulling it down when the momentary buttons are not pushed. In turn, forcing the PNPs to conduct. Let's zoom out so we can get a sense of how that looks in relation to everything else. That's how it looks. Now, we'll need to add those wires from these Schottky diodes down to these 330 ohm resistors. Let's look back at the schematic, verify that. According to the schematic, we'll need two pieces of wire, one going from the cathode leg of this diode down to the same row that one of the legs of the 330 ohm resistors in, and we need the same thing going from the cathode of the upper diode down to the 330 ohm resistor connected to the base of the second PNP. We need these pieces of wire, as well as notice that we need a piece of wire from the collector of the first PNP down to the emitter of the second PNP. We need to connect those two together. So let's add that wire. First thing we'll do is add a piece of wire from this cathode, the rail that the cathode of this diode's in, from here down to this leg, or the rail that this leg of the 330 ohm resistor's in. We'll just run a piece of wire from here to here, like that. We just have a piece of wire from the cathode of this diode. It's connecting the cathode of the diode to this leg and this rail with a 330 ohm resistor. We repeat the same procedure from this rail down to that rail, like that. Zoom out a little bit. Now we've taken care of the wire from our momentary button through the Schottky diode down to the base resistor of the second PNP, from the second momentary button, second Schottky diode, through a piece of wire to the base of the first PNP. Now we need to connect the collector of the first PNP needs to be connected through a piece of wire to the emitter of the second PNP. We need a piece of wire from here to here, like that. So now we have these two PNP transistors are in a series, VCCs, sitting at the emitter of the first PNP, and given that its base will be pulled down to ground through this 10K, it'll conduct through this wire. The base of this PNP is pulled down through a 10K, so it'll conduct as well when neither of the momentary buttons is being pushed. So they're in a series. Imagine two switches being flipped on in a single line of wire. Back to the schematic. Now we can make our final connections. At the collector of the second PNP, we need a 10K resistor to ground, as well as in the same row as the collector, we'll need a 1K resistor through our output indicator LED to ground. It's the last connections we need to make. Here's our second PNP, its collector leg. We need a 10K in this rail to ground. 10K from the collector of the second PNP to ground. it pulls the output low when you shut off both of these PNPs, so that whatever you connect, in this case we're going to be connecting a blue LED and a resistor, but this transistor is useful in that it keeps a constant state even when you disconnect the bases of those two PNPs through these momentary buttons. Your output will be pulled low. Now we can add in this same rail as the 10K and the collector, the second PNP, we can add in a resistor and our LED to ground. I'm using a sort of super bright blue LED, so I'm using a little larger value than a 1K, but 1K resistors perfectly fine for most LEDs you would try to use. Here's a resistor for our output indicator LED, and here's our output indicator LED. Paying attention to which is the cathode, which is the anode. The cathode is indicated by a flat spot on most LED housings. We'll want to put the cathode leg in the ground rail, the anode leg in the same rail as our resistor for the LED. And if we've done everything correctly, this should still function as a NOR gate. Let's see. Connected the 6-volt power supply, and turn on the power. The output indicator LED comes on, which is what it's supposed to do. When both of its inputs are low, the output of a NOR gate is high. Now, does it still go through the truth table? If your first input is high, your second is low, the output LED should be off. And it is. The next option is your second input is high, your first input's low, your output should be low. And it is. And then what happens when both inputs are high? The output should be low. And it is. So we've effectively built a NOR gate using a PNP style transistors and some other components, some schottky diodes and momentary buttons. But I hope this video has been helpful. If so, please consider subscribing to my channel and also consider clicking like on the video. Until next time.